Okay, this is Gaylon Baumgardner, and I know you're with Paragon. I think Paragon Laboratories.
Paragon,
is that correct?
Technical Services.
Technical Services. Gaylon has been doing a lot of work with the incorporation of ground tire rubber in asphalt, and is going to speak about the nature of the interaction of the rubber with the asphalt, and about this idea of vulcanization and devulcanization, which seems to be, to some people, kind of a little mysterious as far as the word devulcanization is concerned. But I'm going to let him explain that. He's a chemist, and he's been doing this for some time. So Gaylon, if you would, I think it would be good if you could explain what you do at the lab. I mean, what I know you're affiliated with Ergon, just what it is you're doing, and then you can move into the more technical side of this.
Thank you, George. As George says, I am Gaylon Baumgardner with Paragon Technical Services, Inc. Paragon is a division of Ergon Asphalt and Emulsions, Inc., which is a division of Ergon Incorporated. Ergon is a major producer of asphalt and modified asphalts in the U.S. paving industry. A lot of polymer modified asphalts, and that's where I'd like to start this discussion, actually, in the fact that we tend to treat ground tire rubber as just a waste product, and it's actually more than a waste product because it's comprised of polymers. So it's a polymer, it's just a post-consumer use polymer that's already been used for another purpose, and there's still polymer functionality that we can use in modification of asphalts. Typically, to give you an idea of the polymers that are in tires, typically tires are comprised of, up to as many as 6 different polymers, depending on which component of the tire we're talking about, whether it's the tread base, the sidewall, the inner liner, the beads, and other components of the tires. The most prevalent polymers in the tire are natural rubber and synthetic rubber, where natural rubber will be polyisoprene or butaperca type rubber or natural rubber, and then synthetic rubber would be styrene butadiene rubber. In the inner liners, for example, you might see more butyl rubber or halogenated butyl because of the impermeability of the material. Naturally, for the inner liner, you want something that's going to hold air, so you would use a material that's more impermeable. So basically what we have when we have ground tire rubber or waste tires is a polymer. Even though it's a post-consumer polymer, it's still a polymer, so that's what we should use, is the functionality of that material. And typically in a tire rubber compound, you have about 30% of that functional material available to use as a polymer modifier for asphalt. So it's my opinion that we should use the tire as a polymer and not necessarily consider it just a waste product. In the formulation of a tire, typically whether it's a car tire or a truck tire, the percentage of natural rubber or synthetic rubber varies. For a car tire, for example, you might have as much as 20% natural rubber and maybe 40% synthetic rubber, and then about 40% or more would be probably sulfur, as the vulcanization and sulfur could be in the presence. I'm sorry, I said sulfur, I meant carbon black, and carbon black would be the reinforcing material of the rubber. There's also other components such as antioxidants, oxidants, accelerators, and sulfur that initiate the reaction of vulcanization. In a truck tire, that's usually reversed. You have about 40% natural rubber and about 20% of the synthetic rubber, and then again about 40% carbon black. So it gives you an idea of what's in the tire. And like I said, the main thing is we should treat it as a polymer and use that functional material that's still left in the tire as a modifier for the asphalt, rather than try to do what some people term is devulcanization. And that's tends to be one of my pet peeves, being a chemist, because devulcanization is technically a misnomer. Because vulcanization is an irreversible reaction. It's used to describe the softening of the vulcanizate or of the vulcanized rubber, or the addition of chemicals such as peroxides to the surface of the rubber to make it more reactive, but you do not devulcanize the rubber. In fact, if you look at American Chemical Society publications, you'll typically see the word devulcanization in quotes, and I'll use air fingers quotes here, because that's the reason they do that, because when you process these vulcanized rubbers to try to devulcanize them, you have no idea which bond or which reaction is occurring in that material, because there's so many reactions that can occur. So they tend to use the quote devulcanization in most of their publications, and basically talk about only two processes that might be devulcanization. One would be the pyrolysis of the rubber, and the second would be the surface treatment of the rubber with peroxides to make it more reactive so that they could use it in other products. One thing that might be good to consider here is that in the tire industry uses about 75% of the synthetic rubber produced for consumer use, and they use 50% of the natural rubber that's gleaned for consumer use. So if devulcanization or a reversible reaction were possible, you can understand why that industry would probably be the main user of the recycled rubber, because they would put it back into tires. And there has been no process to date that will be able, you can take the vulcanized rubber and basically turn it back to the state that you can use it as fresh rubber. I'd like to use an example on the board here, just using polyisoprene as the example. If you look at
Hang on just a second. I'm going to move over here.
And I'm going to use this example to based on a friend and a colleague of mine's comment that kind of gives you an idea of what goes on with this quote devulcanization process. First, if we look at, and we can look at several polymers, I just happen to use polyisoprene as the example because it's the easiest to use. But if you look at the representation of the polyisoprene molecule, where the N represents that there's many repeating units of this particular chemical structure with the double bond. So the double bond is the reactive portion of that polyisoprene structure. And then we look at sulfur, which is the typical octasulfur with the seven sulfur molecules. And we react the sulfur with the polyisoprene, we get basically...
I'm moving back here now, so just hang on just a second. I'll get everything in view here. Okay, I've got it now.
Basically a reaction of the polyisoprene, a cross-linking reaction or a vulcanization reaction, where we have the 8 sulfurs in the reaction, plus you have the chains of the polyisoprene. Now this is a very simple chemical reaction of polyisoprene and sulfur, but in a tire there's a whole lot more that goes on than that. There's not just the sulfur that's reacted from the elemental sulfur that's added for vulcanization. There's also sulfur present on the carbon black, along with other type of reactants on the surface of the carbon black. Depending on what kind of carbon black they use, typically there are 3 different grades of carbon black. Carbon black is graded by the letter N, which means it's normally processed or normally cured, if you will. And then there are 3 numbers. The first number is a representation of the particle size of the carbon black. The finer the particle size, the more abrasion resistant it is, and the more reinforcing it is, because there's more surface area. The coarser, which would be like an N770, something like that, it's less abrasive resistant, and it's also less reinforcing. So you can imagine why they would put the N100 series in a tread where they might put the N700 in the inner liner. Just gives you an example of a carbon black. But the main thing I want you to understand is there's not just this reaction of sulfur and the polymer, there's also the reaction with the carbon black. But to make this all a little more simple, you look at this, this kind of looks like a chain link fence. Or if not a chain link fence, it looks a lot like a net wire fence, where you see the sulfur wires that are holding together the linear wires of the polymer. Well, a friend of mine, Dr. Kodran Duranga, gives the example that if you were to look at devulcanization, it's like you take this fence and we grab it in each end and we start shaking. We start shaking, whether we're doing that with heat or water or whatever type of reaction, we start shaking. Like the American Chemical Society definition of quote devulcanization is you don't know which bonds are breaking. We don't know whether we're breaking the sulfur-sulfur bond or whether we're breaking a carbon-carbon double bond, which is the most reactive bonds that are in there are the carbon-carbon double bonds, which might mean that they would break. And now you have cross-linking, but it's not sulfur cross-linking, it's just cross-linking of the carbons with one another, what have you. Get this right here. Just to give you the example of the type cross-linking that could occur, because you don't know what's occurring. And also this sulfur, if you break this sulfur bond, it's free to react again with another one of these double bonds so that you get more reaction. So the key is that you really don't know what is quote breaking in this devulcanization process. So devulcanization is not a reversible process. I mean, vulcanization is not a reversible process. If it was, we could take this massive structure here, go all the way back, and have this, and that's not possible.
Okay. So under any scheme today, whatever a person might say about this, as you say, you're not able to take the vulcanized rubber and actually devulcanize it back into its original constituents, as you're showing over here on the left. So I guess my question to you is, there are many processors who do many things with rubber in asphalt. Now, the processor I'm most familiar with will say we heat it up, the rubber is like a sponge with asphalt, and it expands, and the net result of the bulk material is different in properties. There are others, however, who go further and actually make the rubber particles much, much smaller. Either they're much smaller going in, or they're in some way milled or commutated in some way. But what you're saying here is somehow, even in very fine form, they're still in there, the rubber part. I'm not trying to put words in your mouth, but,
No, that's correct.
but you can get to the point where you can't, just because you can't see them in some of these products doesn't mean that they're not there.
Let me make another quick example. If I go back to the same structure that I had here earlier,
Right?
and let's just say this is what was in the asphalt.
Right.
When I modify asphalt with polymers, this butadiene, or this double bond, for example, in a polybutadiene, it's the double bond that's the functional site that's on that polymer that allows me to modify the asphalt. That's the functional part that I'm working with. Well, when I vulcanize rubber, I have a lot of those functional sites still available. It's not that I used them all up when I did the vulcanization process. They're still there. That's what I mean when I say there's 30% functionality left in the rubber. So when you start trying to do the devulcanization, so to speak, well, yeah, one thing you might be doing is you might be breaking these into a smaller section, but you still have components that have this double bonded material. The more you destroy these double bonds, the less functional that rubber is. So that's why I say treat it like a polymer, and you use it as a modifier, and this is your functionality, or that 30% functionality that I'm talking about with the rubber, and that's what you're using to modify your asphalt. When you try to devulcanize or you destroy that functionality, now basically you just have a filler that you're putting in the asphalt. You're not getting the modifying properties from the rubber properties or the polymer properties of the rubber. And depending on whether it's polyisoprene or styrene butadiene rubber or what have you, that determines what the functionality of that particular reclaimed rubber is. I think that one of the things that we're looking at and studying now is to see which is the component that's giving the most functionality. Is it the natural rubber or the synthetic rubber? Recent work I've seen shows that there is an effect on how much natural versus synthetic rubber is in the reclaimed rubber, and how it affects asphalt and how compatible it is with asphalt. So yes, to answer your question, maybe in some of this making the chain shorter, basically what we might have is, rather than having this chain, we may have done just as Codron says, is we break that bond, and now what we have, rather than having this big structure, we've got a smaller structure, but we still have that double bond functionality that we can use to modify the asphalt.
Obviously, this is a very complicated chemical story for sure, and I thank you so much for sharing your thoughts. I know, to condense it down into a little easier, digestible way of saying it and representing it. I know, on the other hand, you're working on some very important research. I know that, and that's going to go into a lot more detail on this, and I look forward to seeing that in the future. And for those of us who are more technically inclined, I'm sure it will go into a great deal more depth and detail. But I thank you very much, Gaylon. I think it's a nice little presentation. We'll do what we can. We may have to come back later and create a graphic, if you understand what I mean, because I know you did your best here, but we may ask you later to come back and maybe make a graphic in the computer or something like that.
Okay.
Thank you again. Very good. Excellent. Thank you.
Thank you.